and take a look at them. And of course, you can always keep working. Thanks, Lauren. All right, so on Monday, we did kind of a review of fractions because that's our very, foundational place that we're building from as far as the math concepts that we're working on and learning this fall semester. Okay. And so today's warm up then is reviewing the major concepts that we went through in the first fall quarter. So if you weren't here when we started back at the end of August, it's okay if these ones felt hard, but I feel like if you have been here, that hopefully these felt mostly like review and you felt like you knew what to do and what was going on. And if not, that's why we review and warm up. Okay, so we have a first question on a biology test with 40 questions. Thurman answered all the questions and answered 6 of them incorrectly. Okay, so the question is, what is Thurman's ratio of correct answers to incorrect answers? Okay, why is D the answer, Ryan?
It would actually takes to or and then it covered or correct 6 graduates.
Beautiful, good. So hopefully you guys caught what Ryan says. So our rules of ratios, right? Order matters. So we first have to figure out how many correct answers Thurman got on the test. Do we directly know that information? Do we directly know he got 34 correct? Really?
No. Incorrect. 6.
Good. So no, it's indirect, right? We only know that there's 6 incorrect, but since we know how many total questions are on the test, when we subtract 40 minus 6, we know that 34 were correct and 6 were incorrect. Okay, so that's the order that we need to put our values in to create this ratio. But then we have to follow the second rule of ratios. So order matters and reduce if you can. And so if you have a ratio of 34 to 6, then you would reduce it by a common factor of 2. 34 divided by 2 is 17. 6 divided by 2 is 3. So our final ratio for Thurman's correct to incorrect answers on his biology test is 17. For every 17 questions he got right, he got 3 wrong. And that's pretty good. So hopefully everyone remembers that. These ratio problems hopefully shouldn't be too hard if you can remember the 2 rules, which I know can be challenging too, because remembering is hard. Okay, everyone okay with this first question? All right. Okay, so next we have number 2, tough guard epoxy is supposed to be mixed in the ratio of 3 parts hardener to 8 parts base. Okay, so once again, we have a ratio 3 to 8, 3 hardener to 8 base. Yes, Ryan? C. Okay, how'd you get C?
Yeah. Now, or baby.
Mm-hmm.
Oh, do it. But,
Good. So you create a proportion, right? You say 3 is to 8 as what is to 40, right? Then you could cross multiply and divide if you wanted, or because these are pretty like common numbers, hopefully, right? You would say, okay, what did I do to my 8 to get it to 40? I multiplied it by 5. So then I just do the same to my other value, right? 3 times 5 is 15. So And I think everyone got that one. I think most everyone, almost everyone. So good job on that. Um, and so that's our proportion, right? Where we have two equivalent ratios set up for each other. And generally we need those ratios, right? Because we need to increase at a certain rate, but keep that ratio intact. Otherwise, our epoxy isn't going to do what we want it to do. All right. Next, Jim types 52 words per minute. So how many words can he type in 26 minutes? B, how'd you get B? Good. So we know Jim's rate, right? His typing rate. And if we multiply his rate times time, then we get, right, we're left with words, right? So hopefully everyone felt good about that. So that's our rate, right? This is still a ratio, 52 words in 1 minute. That seems really fast. I don't know. I'm not an accurate typer, so I don't ever feel like I'm a fast typer. But yeah, if you could type that many words in less than half an hour, it feels pretty good. But yeah, so does everyone recognize the rate here and then using that rate to apply it? So once again, you could set up the proportion, right? 52 words is to 1 minute, as how many words is to 26 minutes. You could cross multiply and divide, but you could also cut out the middle person and just multiply the rate times the time. Yes?
Nah. What?
Okay. Did I mess it up?
Yeah.
Really?
Good. Breathe. Yes, breathe. See.
You got 0.3.
Yeah. Not three. Just three.
Just 3? Hmm.
That's the same thing I got to.
Okay.
We just proved.
Okay. What did you put as your numerator?
I did 34 divided by 11 by.
Why are you taking the original amount and dividing it by the amount of change? You aren't following the formula. That's okay. No, you're not dumb. I'm just saying that I was like, well, if you're getting a whole number, remember that if the question is asking for a percent, right? Like a percent drop, a percent decrease or increase, then your answer needs to be, right, less than 1, but greater than 0, right? To represent that percentage. Yes, Ryan?
In the car, you were down.
That's okay. Oh, Quentin? Oh, Quentin? Yeah, no, he's good. Yeah. It's okay because this was, one of the last things we did before break. We didn't maybe get as much time to practice this one. And this question's a little different than some of the other questions we've seen, but hopefully you noticed. So in a normal season, the Seaside Resort has 34,500 visitors. This year, due to bad weather, 11,500 fewer visitors came to the resort. So oftentimes it would say like this year due to bad weather, what would it be? Like 22,000. So they actually saved us a step that we were usually having to do, which was to subtract, right, the two values to get the amount of change, right? But here they tell us directly the amount of change because they tell us how many fewer visitors came. So only 23,000 came this year, okay? but we need this number here, the difference, right, between the original amount and the new amount, which is our amount of change. Okay. So 11,500 divided by 34,500, which was our original amount, right? Our normal expected amount of visitors, okay? But this year we had 11,500 fewer visitors, and so the percent change is 33.33%. Because hopefully you guys remember, right? These are our thirds, so they make kind of crazy percents and decimals, but 0.33333333 onto infinity is the same as 1/3. Okay. So if you need to, sometimes there's an additional step, but other times you might have to subtract the two values and then divide by the original value. Okay. So does everyone hopefully is kind of remembering and seeing how this problem works? Are there questions or other thoughts? Ryan, you feel a little bit better about how the problem works? Good. Okay. All right. So good warm up, everyone. We'll, of course, try to do more review of these problems just to make sure everyone's, staying fresh with that as we build more new knowledge into what we're doing and learning. But hopefully you guys are seeing this connection between how all of this kind of works off of fraction-y stuff too. I think I just made up a new word. So, all right, good. Okay. All right. Well, let's hop into our lesson then and go back to where we left off. So I think it's page 67. What did I do?
Stuff from last semester.
Yeah, it's the same book. Yeah. And of course, remember that if you miss the beginning of math classes, or if you have some time, you can always go back and work on whatever we didn't, do as a class or group in units 1 and 2, or you can work ahead as well. So unit 3 is looking at the concept of probability, but before we get into probability, we're going to kind of, once again, kind of start from the start. And so probability has to do with using the possible ways we could count something that could happen and trying to kind of decide how likely or unlikely it is to happen. But before we get into that, we want to just work on looking at the amount of possibilities that exist when we begin to ask how many different ways, right, can we organize something depending on certain criteria. So that's what we're going to start with these counting strategies. And the first sets of problems we looked at are pretty straightforward. And so you don't necessarily need a lot of math if you have good common sense and good kind of diagramming or mapping skills. So our example style problems that we're going to encounter is like what we see here. So the Parkers are taking a photograph of their 4 children. They plan to stand in a line. So how many different ways can the children line up? Okay. So that ends up being our question there. And so with this problem, you could, once again, just try to write out the number of combinations, and then it tells us, right? If we're able to carefully organize the work, you can begin to see a pattern that will help you will help you count the possibilities. And so if you start with Alan as the first position in the photo, right, and then rearrange the other three siblings, you notice that if Alan is in position 1, then there's 6 possible arrangements. And then as we map it out with Bianca in position 1, we find the same pattern exists. So we can then conclude, right, that for each child, right, there's 6 possible combinations with each child in that first position. And so since we have 6 possible combinations and 4 children, 6 times 4 is 24. So we have 24 possible ways. Yes, Ryan?
Should there ought to be three,
Why?
okay, there's a more kids or eight, or 8 kid.
Yeah, but right. So I can start by going A, B, C, D, and then I could go A, B, D, C. Then I can move Callie into the second slot, and I still have 2 combinations between Bianca and Dennis in the second spot.
Wow, you know, and
Yep. So it ends up being 6 per kid in that first spot. And so, yeah, so they kind of said, the best way to make sure that I'm arranging this correctly, because it can get messy, right? When you're diagramming this out. So start with AB, AB, AC, AC, AD, AD, right? BA, BA, BC, BC. So you can see that they try to find that pattern, and it's not easy. Uh-oh. I don't know why it keeps doing that. But once again, since we know that there's 6 possible combinations per child, we have 4 children, we have 24 total possible ways that we could line up the kids for the photo. Okay. Sometimes, depending on the factors that you have, a diagram might be more helpful than these kinds of lists, but they're basically, to me, look very similarly organized. But here we have the example of Emily. She wants to wear red, white, and blue for a holiday. She can choose from 2 pairs of sneakers. So we always kind of start with our smallest kind of amount in our category, right? And then break it out from there, okay? She has 3 red shirts, she has 3 shirts and 3 pairs of shorts, all of those 3 colors. And each outfit, right, needs to have 1 of each color. So that's kind of the rule, right, of the combination. So once you figure out that if she only has white shoes and blue shoes, then that means that that's kind of where it starts, right? And so if she wears white shoes, then she has to wear blue or red shorts and a blue or red shirt, vice versa, white and red for the blue shoes. And so it ends up being a combination of 4 possible outfits with those clothes, okay? So sometimes just a diagram can help you count it out. You don't have to really worry about math. So we went through some of these together. So if you guys want to go back and work on these or try them out again, I would say go for it. The answers are in the back, okay? But remember that the goal here is to figure out how to map it out, okay? And to find those patterns and use that to help you get your answers, okay? But let's go ahead and look at page 66. I think we kind of started here or we got this far on Tuesday, but
Well,
you lost it? Oh my God. I don't know if I actually have another one. I'll have to look for one, but let me. Okay, so let's go ahead and go back to where we kind of left off. So the first kind of problems that we're working with are called permutations. So you don't necessarily need to know that word, but there's kind of two styles of problem that we're going to look at. Okay. So the most important thing is, right, when order matters, okay, then we're doing permutations. Okay. And so they give us this example of a combination lock. A combination lock is actually a permutation. It's not a combination. A combination is going to be what we're going to label a different type of problem. But when you use a combination lock, you have to enter the numbers in a certain order, right? And so because order matters on a combination lock, it's a permutation, that sequence of numbers and the possible number of combinations that the lock could have, okay? And so that's why a combination lock should really be called a permutation lock. So we can go around, making fun of people who don't know it's a permutation lock, I guess. But let's look at how the problem works, okay? So go ahead and look at that first example.
Anyone else in the class need, do you need a copy of this? Make a copy of it? There. We need to pull it out.
Uh-oh. My
Printer, kind of shaking or something to get that line out of there. Sorry about that.
Okay. Hopefully that line is okay. Yeah, it's right there. Okay, so an example of a permutation problem: in how many different ways can a student arrange 5 different books on a shelf? Okay, and so count the number of choices the student has for each space on the shelf, right? So we have, right, basically kind of like 5 little sections or 5 possible locations for each of the 5 books, okay? So for the first book, right, we have 5 books to choose from to put into that slot or spots, right? But after the book is placed in the first position, now when we move to the second position, we only have 4 books to choose from, right? Because one book is already locked into that first spot, okay? And so then after each book is placed, there's 1 fewer choice, right? So basically we go from 5 choices to 4 choices to 3 choices to 2 choices to 1 choice, okay? And so once you get your kind of the amount of choices possible in each of your kind of spots, then you multiply those numbers together. And so for this problem, we have 120 different ways that the 5 books can be arranged on the shelf. Okay? Is that making sense for most people? Like, this was kind of a newer math type thinking for me when I started teaching this stuff. So, hopefully it's making sense why we're doing what we're doing and how we figure out kind of the number of possibilities for each slot. Okay. And then by multiplying them together, right, we're basically saying, you know, that you're mixing them all which ways. Okay. So to solve the permutation problem, you multiply the choices. Okay. So if we look at the next example at the bottom of page 66, okay, we have 15 runners in a race. And then it asks, how many different finishes can there be for first, second, and third places? Okay, so we're not, yes, Ryan?
I think it's 9.
9 what?
Oh,
Okay. What are you multiplying to get 9?
great time. Pretty.
Okay. But you have 15 total runners that could fill those 3 spaces in multiple different ways, right? You know,
Okay.
so it's going to be, so hopefully you guys are seeing how this is going to be kind of big numbers. So, you know, we first could kind of write them out if it was something like 24 combinations, but now when we're starting to deal with 15 different things to move around, then we're going to end up with a lot of possibilities, okay? So we count the number of choices, so we know that, right? In first place, there could be any one of the 15 runners, right, could get first place. So there's going to be 15 possibilities in that first place slot. Yes, Ryan?
So 15 times, 14 times, 13.
Yes, look at step 2.
Yo, it's my fun.
Sorry, I always just match the volume of your voice because I have a booming, loud voice, and I wish that I had a friend. I'm so sorry. There you go. There you go. I'm sorry, I'm really not making fun of you. I'm sorry. I usually just used to doing that when I have very quiet, timid students. But yes, you're correct. So, yep. So basically we have 3 slots that we're interested in for this. And we know that in the first spot, there's 15 possibilities, second spot, 14, third spot, 13. So then we multiply those 3 values together. And so if we have 15 runners in a race, there are 2,730 ways that those 15 people could finish first, second, and third. Okay. So the math part isn't hard because it's mostly just multiplying, and you'll of course most likely want to use your calculator. I would say absolutely want to use your calculator. I don't want to multiply those 3 big numbers together. All right. So hopefully everyone's feeling good about examples 1 and 2. Stop me if you have any other questions or anything, okay? All right, and then finally, let's look at this last one here. So will the choices always count down? And it tells us not always, okay? So hopefully you guys agree in the first 2 scenarios, right? 1, the position of 1 in the kind of that first spot, right, affects the remaining spots, okay? But that's not always the case, okay? So here we have a byte combination lock that has 3 dials, and they each have 10 numbers, right? So you have dial 1, dial 2, and dial 3. And because, right, what I dial in for number 1 does not affect what I dial in for number 2 or number 3 on this style of lock, right? then 10 goes in each of my spots there, because for each of my dials, I have 10 possible choices. Okay? But then we still do our multiplying. 10 times 10 times 10 is 1,000. So we have 1,000 possible combinations that we could set that lock to. Okay?
I want to do this.
Where are you feeling like it's getting funky?
How can you have 1,000? Okay.
Well, that's because you have 10 3 times, right? So I have 10 choices on my top,
Why is it 30?
because for every click of one dial, I could click the other dial. So it's like it's multiplying, it's not just adding. I'll have to work on that. I'm sure you will. I'm sure you will. Let's look at these 4 practice problems here. Do you guys want to try them on your own, or do you want to keep talking about them as a group?
Group.
Okay. No, you're fine. Okay, let's look at problem 1. Okay. So Jasmine has 8 songs in a playlist. So that's kind of our total amount. The playlist is set to play songs randomly. So if she listens to 3 of the 8 songs, how many different orders are possible if a song may not be repeated?
See, it's all confusing.
Just the wording?
Yeah.
Okay. So we have to think about, okay, what's kind of our scenario here? Oops, not a touch screen. So, right, we know that she's gonna listen to just 3 songs. So we have kind of 3 spots, right? We have song 1 that she's gonna listen to, song 2 that she's gonna listen to, and song number 3. Okay. Now, how many total possible songs could she listen to?
27?
How are you getting 27?
Is it 3 times 3 times 3 or 8 times 8?
Well, remember that, sorry, I'm looking wrong, right? A song cannot be repeated.
So we'll go like 8, 7, and 6, right?
Yep. Good job, Clinton. Good. So for the first of the songs she's gonna listen to out of the 8, there's 8 possible choices of song. But since we can't repeat, by the second song, she's down to 7 choices of song, right? And then by the third song, since it's not gonna repeat. So who can tell me what 8 times 7 times 6 is? Thank you. You guys agree with Quentin, 336?
No.
That wasn't a very confident no, Ryan. Oh. Sorry. So yeah. So for number 1, we end up with, right, 336 possible song combinations. Okay. So does that make sense? So you kind of have to map out your situation and then figure out how many choices do I have here? Does that affect how many choices I have here? And that's where we have to decide yes or no. Okay. And that's where you have to, unfortunately, read carefully, which can be.
Did I say not repeated and then
Right. So if it could repeat, then you'd have to do 888 because, but hopefully no one, well, I'm like, no one listens to songs on repeat. And I'm like, oh wait, my best friend in high school used to do that all the time and drive me crazy. But I'm still here today. And I always wonder if she still does that. Okay. So everyone feel okay about number 1? Let's look at number 2. Okay. And we'll keep trucking. All right. So a company assigns a code to each customer. The code has 2 letters followed by a single digit number from 1 to 9. Okay, so once again, it's like our slots here, right? We're making this customer code. And the code is letter number. Okay. So does everyone see how the code is creating kind of our little slots here, right? Okay. And so if the letters must be different, okay, so we know that letter 1, right, can't be repeated in letter 2, and we only have one number, 1 through 9, right? So there's 9 total number choices. How many possible choices are there for the first letter of the customer code?
26.
26, good. And if the letters must be different, how many choices do we have for the second letter? Good. And then all we gotta do is plug and chug. So what is 25 times 24 times 9? I'm sorry, I'll have to, 5,500 and,
850.
oh, 5,850? Did I get the number right? I'm sorry, I'm still,
Yeah.
okay, thank you, sorry. So I guess once they get over 5,850 customers, they're gonna have to come up with a new system. All right, how do you guys feel after number 2? Better, worse, same?
Better, plain. God, that's so good.
Okay, no problem. I know these ones are, like I said, even for me, I've had to work really hard to feel like I could do them okay, and I still don't feel very confident. All right. So for summer reading, Grace must choose 4 out of a reading list of 12 books. How many different ways could Grace complete the assignment? And I'm assuming she's not going to read the same book twice. I think that's safe to say. So how many different spots do we kind of need to fill in with our possible choices? 4, good, right? To represent the 4 books that Grace is going to read. There's book 1. All right, and so starting with book 1, how many possible choices does Grace have? 12. And for book 2? 8,880. Got it. Thank you. Good job. Did I do the? Well, I thought that's what you said, Quentin. Did you say 8,880? Or did I hear that incorrectly?
It's 11,000.
Oh, 11,880. Okay. I just didn't hear the beginning. Thank you. All right. You guys want to try number 4 on your own first?
Yeah.
Awesome.
$100. That was it.
All right, how are you guys doing on this one? If you're on, you got it? Okay.
Very smart.
What do you guys think? Do you agree with Ryan? 120 for number 4? How'd you get 120? Beautiful. Good. And so that was like our kind of first example there. But yep, exactly. So there's 120 right, combos or orders, I guess. Good. So yeah, luckily, at least these first ones, it's pretty straightforward, these permutations, once you kind of get down what you have to look for and how to organize it. How are you guys on Zoom doing? Hanging in there? Feeling okay? Is this making sense? Cool. All right, let's keep trucking. So like I said, do you guys feel like we need to do more of these problems, or do you want to do those 5 problems for homework? I think you guys could do them for homework now if you wanted.
No,
No, what was that?
no.
You're down for homework?
Yeah.
Okay. So go ahead and try those 5 problems at the bottom of 67 for homework. The answers are at the end of the unit in your book. So you should be able to check your answers. Okay. But let's go ahead and look at the next piece. And this is, I think you guys are doing okay with permutations, but of course we'll go back and practice. Okay. All right. So a combination is an arrangement of items in a set in which the order of the items doesn't matter. Okay. So let's see if we can get a sense of how this works and how it's different from permutations. Okay. So now we have this scenario. There are 8 workers in an office and the fire safety team needs 3 people. So the manager puts the 8 workers' names on slips of paper and randomly chooses 3 names. Does the order of the names are chosen make a difference?
No.
No, right? Because they're all just a group. The order doesn't matter. We just need 3 of the 8, and it doesn't necessarily matter. Okay. And so, so the order doesn't matter, right? We could have chosen Letitia, Calvin, and Joshua, but we could have also chosen Joshua, then Letitia, then Calvin, and it would have kind of worked out the same. Okay. So for these combination problems where order doesn't matter, so that's always going to be our first kind of thing we're going to have to work on. Is this a permutation and order matters, or is it a combination and it doesn't? Okay. So first we find our permutation, right? Right? For the first person chosen, we have 8 possibilities. For the second person chosen, we have 7 possibilities. And for the third person chosen, we have 6 possibilities. Okay. But then we have to do an additional step. Okay, so this was what we have been doing, right? When order mattered. Okay, but now we have a second step. Now we have to find the permutations for a group of 3. And we're finding how many different ways 3 names could be arranged. Okay, so this is our total people kind of in the pot. And then here's kind of how the spots of the pot work out, right? And that for the first names, right, we have, three possibilities, then we have two possibilities, then we have one possibility. Okay? Then we take our total permutations from the total group and divide by our number of ways that it can be arranged. And so there are 56 possible combinations of 3 out of 8 employees to be on the fire safety team. Okay? Yes, Ryan.
But remain,
What about what remainder?
remainder 7.
The remaining 7 where?
Right next, 6.
So you're saying 336 doesn't evenly divide into 6? So now to our initial multiplying step, we have kind of another permutation that we'll need to calculate that becomes the denominator, and then we divide, okay? So we have kind of 2 multiplying steps now and a dividing step for a combination. And remember, this is when order doesn't matter, okay? So let's look at these 6 scenarios here. And they don't necessarily want us to do the math, although we can, of course, but we first need to determine, are we dealing with a permutation situation or a combination situation? Okay. Great, sorry, I just want to make sure. Okay. So in a lottery, you win a prize if you can guess which 6 balls will be numbered from 30 balls numbered 1 through 30. So does order matter? Does the order in which the balls are drawn matter? No. So it's a combination problem. Okay. And it would be pretty complex, right? Because we'd have to do 30 times 29 times, we'd have to do 6 of those, and then our 6 balls and divide. So good. So good. So this is a combination problem. Order doesn't matter. Okay. Okay. All right. Number 2. A class president and secretary will be randomly chosen from a class of 20 students.
Oh. Who?
Well, does the order matter in this scenario?
Oh.
Well, are they going to choose class president first and then secretary? Or are they just going to pull out 2 names and they're together? Because remember up here, right, they were chosen randomly, but they're all kind of equal on a team. Is that the same thing going on here?
Yeah.
I mean, we probably would need more information. But once again, right, we would assume that order does matter because we're going to randomly select the president and then select the secretary. At least that's what the answer said. The order the students are chosen will decide who is president and who is secretary. Okay. So
I have to be 40, correct?
it would be 20 times 19. Why two?
Because every morning there's 12 each.
Well, there's two, yeah, I mean, there's two slots, right? But then you have to fill in the amount, right? So for the president slot, there's 20. And for the secretary spot, there's 19.
It's gotta happen. There's 2 people for every one slot. Right? If it's a rhythm.
That's okay. Well, let's look at number 3. A phone company generates new numbers for an area based on the last 4 digits in a telephone number. Do the order of the last 4 digits in a telephone number matter? Do you have to put them in the right order?
Yeah.
Yeah. So does that mean it's a permutation or a combination?
Permutation.
Permutation, good. Beautiful. Okay. How about number 4? 3 scoops of different flavors of ice cream are placed in a bowl to make a sundae. Do we have to put the scoops of ice cream in a particular order?
No.
No. Only unless you really, really, really know how that's going to affect it. But yes, so here we have a combination, right? All right. A baseball manager chooses 3 players from a group of 15 to bat in the first, second, and third spots in the lineup.
Permutation.
Okay, why do you think it's a permutation? Whitney?
I would choose 3 players out of it, so those same players can. So, right?
Well, that's going to happen if it was either a permutation or combination, but does the order that the 3 players are put into matter?
Yes.
Someone's got to be first, someone's got to be second, someone's got to be third. And generally, right, when you create a lineup for a baseball game, I think you have to keep everyone in the same batting order or get in trouble. At least that's how it used to be when I played in the long, long ago. So here order matters, right? The order that the 3 players are put into matters. Okay. Once again, it doesn't matter if I put the chocolate in the middle of my sundae as the right scoop or the left scoop or the middle scoop. As long as there's a scoop of chocolate in there, my sundae is going to be amazing. Okay, but here we have specific order. Okay. But it's tricky, Brian. I like I said, I'm cheating right now and making sure that I'm getting this right. So don't feel bad. Okay, number 6, 5 basketball players are chosen from a group of 12 to start the game. Does the order matter for these players?
No.
No. Good. Why do you say no, Ryan?
Everyone.
Right, exactly. Each player chosen is starting, but it doesn't matter what position they're starting in, only those 5 are starting, right? Okay, so now that we know what kind of scenario we have, let's think about our math. Okay. All right, so we know for our combination, like we said, this one's going to be pretty long because we have 6, right? We have 6 spots. So it's like And we have 1 through 30, right? So for our permutation for our totals, let's see if we can. Sorry, my twos are not consistent. One. So there's 6 there. And then, right, we're gonna divide by, right? Oh, thank you goodness. I was like, wait a minute. Ah, darn it. Was doing so good too. Uno tres. Hopefully you guys got that. Sorry. Okay, one more time. Don't skip the 4. I don't know what happened. Did anyone get an answer yet? So if you were gonna try and type all of this into your calculator, you would have to use like parentheses and stuff. So I would just multiply your top numbers, multiply your bottom numbers, then divide. Did anyone get an answer yet? Yeah? What'd you get?
7.
I'm gonna say that's probably not the right answer. Or I should start playing the lottery. So-
60,000,
Pardon?
593,000.
Is that just the top number or did you do the dividing? Okay. I believe you. It's okay. Does everyone see how I set up the combination? And then 6 times 5 times 4 times 2. So you have 42,710,000 divided by 720. Yep. So there are 593,775 possible orders, right? That the 6 lottery balls could be drawn. So is that what you got again, Rob? You got
Yes.
okay, good. Good. So, like I said, definitely gonna be on the calculator section. You probably wouldn't see this. Let's look at number 4 since it's right here. So how would we work out our scoops of ice cream? Although it doesn't tell us how much total choices of ice cream we have. So we might not be able to do number 4. We might not have enough information. Yeah, because you'd have to do something like. Well, let's say that we're at Baskin Robbins. So if we have our 31 different flavors of ice cream and we could say something like, you have to have, right, 3 different scoops or 3 different flavors or something like that. Then you would have. Still gonna have a lot of combinations. All right, did anyone calculate number 4 here? I got, huh? I got 4,495. Is that what you said?
For number 4?
For number 4? Yeah. If we were at Baskin Robbins, right? And the only problem with number 4 is we couldn't, if this was all we were given, we'd probably have to answer there's not enough information because we have to have, right, a total number of flavors. So I was saying, right, that we're at Baskin Robbins. So there's 31 different flavors of ice cream. And so if there are, right, then that means our permutation, we have 31 choices for scoop 1, 30 choices for scoop 2, 29 choices for scoop 3. And then, right, we have our slots 3 times 2 times 1. And when we divide that, we end up with 4,495, right, combinations of ice cream. 3 scoops of different flavors of ice cream.
I was thinking of Cold Stone.
Yeah, they definitely have fewer flavors, but then toppings would be where those combinations would get pretty intense. Oh, I am in a Cold Stone. Yeah, milkshake sounds good. What happens when we're doing this before lunch? Okay, everyone feel okay about number 1 and number 4, hopefully? Let's look at number 2. Go ahead and try number 2 and number 5. Now, these are just permutations, so we only have to do the multiplying and not the dividing step. Oops. Don't need to do that. Hmm? You confused yourself?
Talking.
Oh, you're talking to yourself. Okay. Dancing with myself.
$8,008.
Okay. For number 2 or number 5?
2.
For 2, you got what?
8,008.
20 times 19?
Every
Okay. Did you just multiply? That's okay. Good. So for number 2, right, we just have those 2 spots and we have 20 total students. So 20 times 19. And so, right, there's 380 possible combinations of the 2 offices. What about for number 5? What answer did you guys get? 2,730. 2,730. And so same thing here, right? Since we have 3 spots in the lineup and we can put 15 of our folks in there, order matters. And so 15 for the first, for the leadoff hitter. Second, I was like, I can't remember the fancy name for that. Almost a cleanup hitter.
On deck.
On deck, yeah, thank you, like, I know you, yeah, it's been a while. Okay. Doing good. All right, let's see. Let's try and squeeze in these last two at the bottom and see how they go. So number 3 and number 6. So one is a permutation here. And then we have a combination for number 6. So just multiplying here. And then, so let's see, generates new numbers for an area based on the last 4 digits in a telephone number. So I guess you would call, right, each of the digits, there's 9, right? Possible digits, 10. Oh yeah, because 0. Yeah, thank you. So, yeah.
10, 9, 8, 7, 6.
Actually, I mean, it doesn't, I mean, I think you could repeat the number, so you could almost just do 10, 10, 10, 10. Yeah, I think that's what I would say for that one. And then, wow. Yeah. The only thing you could also say is, well, technically the first number can't be a 0, but I don't know. Or no, these are the last 4. I think that makes sense. And then here, since we have a combination, we would do 12 times. Whoops. Times 9 times 8. Oops. Is anyone crunching number 6 there? No, you're good. I'm glad that you can be amused. Oh, 900.
Gee,
You guys getting these numbers for 3 and 6? Sorry if I'm going fast here at the end. I'm giving you the answer. All right. Think we're at a good spot. So like I said, go back and do those 5 problems on 67. Those are permutation problems, and then we'll pick it up here on Tuesday on 69, but you can work ahead as well if you'd like. So sound good? Everyone on Zoom okay? Any questions, confusions? You guys were, like I said, it's okay that it's a mellow Thursday. Okay, good, Lauren, good to hear. Thank you, Lance. All right, I am available tomorrow if anyone needs to come in and do anything extra. Be crafted tests or getting kind of extra help. should be around from 10 to 6. Did you get the online lessons email or? Okay, no worries. I did get it set up for you there, but, oh, rush or pressure.
I take a math test tomorrow.
Another practice test? Sure. You-
Yeah, remember you gave me some study material.
Oh,
I'll go over
okay.
that tonight.
Okay.
When's
yeah.
Last time.
Probably like 10. I mean, I'll get in at 10. So if you want to come a little after 10.
Sure,
Yeah.
okay, thank you.
Yeah, of course.
Bye, Julie.
Mhm. This one.
No.
Oh, maybe. I think it's this one.
Oh, okay. Yeah, that's what we mind of.
Yeah, yeah. There are two different books, you can kind of tell.
Okay.
But yeah, thank you for checking. Okay. Diane, you good? So?
Yeah.
Okay. Well, it's nice to see you. We'll see you next week, okay? Yeah, there's that rock I keep sitting on. Mhm.
Yeah.